Hey class, what's going on? Week 2, video 2, I'm not quite sure. Yeah, it must be video 2 because you absolutely handled Ohm's Law in the last video. You guys got it nailed down pat, I'm sure. You destroyed it, you slayed it, you obliterated it, you annihilated it, you took its lunch money, you said unkind things about its mother, all that stuff. All that to be said, even though you handled Ohm's Law, we're about to get a little deeper right now. We're about to take it one level further. This is like Inception, and it's about to get real. All right, I'm making it a lot bigger than it is. It's not really that bad. But let's get into it. Let's figure out what we're working with. All right, so in this video, I'm going to try and keep it short, and we're going to go through a bunch of problems together. But we're going to be talking about series circuits and parallel circuits, how they compare and how they contrast. And we're also going to be talking about Kirchhoff's law a little bit. I don't care if you know it in name. What really matters to me that you understand it in principle. And we'll talk about it as we go through the problems, but as long as you understand the rationale why it's behaving the way it is, that's what matters to me. Let's get this out of the way. Groovy. All right, series versus parallel circuits. So we've already gone through a simple circuit. Sometimes it's called a theoretical circuit. It's basically a circuit that's got nothing to it. It consists of a source, which is our battery, and it has at least a component in it, and there's a load connected by two wires. You're going to see this little diagram here. This icon is new. In diagram models, that's called the lamp. It really just refers to a load or a pull on the circuit. And that's all that means. So you'll see that more frequently from here on out. It just means that there's something that's pulling the energy or using up the energy in the circuit. So let's move on to what a series circuit is. A series circuit includes more than one component, but only one path for the current to go through. So the current is guaranteed to hit every component in its full loop around the circuit. A parallel circuit is a little different. That's when two or more components are connected, but the current can flow through one component first without going through the other ones. And you can see on the far right, that's what they look like. There's several different paths for the current to go through in the circuit. It's not relegated to just one straight shot. All right, so let's learn some individual characteristics of these, and then we'll get into how we're going to use them. All right, let's get into some additional characteristics of a series circuit. In a series circuit, much like what we've heard before, if resistance increases, right, the barrier to the flow of electricity, if that increases, then it's going to decrease the amount of current. It's going to decrease the quantity of electricity flowing through a circuit. It's important to note, however, and for those of you taking this test coming up, it is important to note, however, that the same amount of current is running across all components. Also, if any component in a series circuit dies, the entire circuit is nullified. It's also dead. All right, here we see a light bulb in a simple circuit. Let's throw a few of them in series. And I want you to note that there's more resistance because there's more components drawing electricity or resisting the flow of electricity within our circuit. So our bulbs are going to be dimmer overall, right? Also, any one component that dies in a series circuit, the whole train wrecked. Everything else is dead as well. Now, what makes a parallel circuit a little different? Let's take a look. All right, same thing, right? As resistance increases, our current is going to decrease, but parallel circuits have the same voltage across all components. Let's try to visualize this. Look at a tributary, right? Even though there's different splits that the water can take, the push of the water at the entryway to those tributaries is going to be the exact same. It doesn't matter how many there are, the force of water pushing them in is going to be the same. Now, they may be smaller or larger river sizes, tributary sizes. I'm not an aquatic specialist. There might be bigger or smaller paths of water. So there might be less or more flow, less or more quantity of water, but the force feeding into those tributaries is all the same. Same as with the parallel circuit. Same amount of voltage across all components in a parallel circuit. I'll say it again for the test. Same amount of voltage across all components in a parallel circuit. Also, if one of your components dies in a parallel circuit, it's not the end of the world. You still have use of the other paths that the current can take. All right, let's get into actually playing around with these on paper and we can see how they behave. It's going to make a lot more sense this way. All right, guys, I would be remiss if I did not go back and view a simple circuit again and take a quick review. So let's do that really quick. Even though I know you guys nailed it and you don't need it, let's do it again just for fun. All right, so here's my, God, that's terrible. Oh, all right, let's not make fun of my drawings tonight. Good deal. All right, here is our simple circuit. Extremely simple. We've got one voltage source. We'll throw 12 volts on this battery. That sounds fun. Mark our terminals. And then we have a singular resistor. We'll call this guy R1. And we'll put this at 4 ohms. That sounds fun. Excellent. All right. So we've got our battery, 12 volts, and a resistor of 4 ohms, and we're trying to figure out how much current is flowing through our simple circuit. And you guys beat me to it. You're awesome. VIR is the formula we're going to use. V is equal to I times R. And let's do some quick substitution here. Our voltage is equal to 12. We do not yet know the current. That's what we're trying to find out. And our resistance is 4 ohms. All right. Let's do some division. We're going to divide 4 on both sides, which gives us 3 is equal to I. And we always measure current in amperage. So 3 amps of current are flowing through our simple circuit. Simple circuit, simple answers, rockin'. All right, now let's kick it up a notch. Whoa, Nelly, here we go. Here is our series circuit. You can see it's a series circuit because there are 3 components that are all in line within the path of electrons. There's no optional course that the electricity can take. And if you remember, we mentioned that current across each series resistor is the exact same. And it sounds counterintuitive, but let's think about it. Let's pretend we're looking at a river from overhead. And we see a couple of boats. Terribly drawn boats that are just awfully drawn boats that are floating in the river. I don't even know what that third one is. It looks like I can't even describe that one. Anyway, so here's our boats. Call these boats R1, R2, and R3. And the river has a current, right? There's a volume of water that's flowing in one direction. It doesn't matter which boat you're in. You can be in boat R1 or R3 or R2. You're still going to feel the same volume of water rushing downriver as you're in the boat. And that's pretty much what's happening with these resistors. When they're in series and there's no other way that the current can go, they're feeling the exact same quantity of electricity rushing through them. You know, some of these boats might be larger. Let's take our really terrible R3 here, and we'll make it, that's a big guy. It might be more of an impediment to the water because it's larger, it takes up more space, but it feels the same flow, the same quantity of water as R1. I hope that makes sense, that analogy there. All right, so now that we have a visual of terribly drawn boats and a terribly drawn river, let's go back to our terribly drawn circuit and take a look at this. All right, so we've got a power source here. We'll throw 60 volts on this guy. this DC power source. And we are on a mission to try to find the current, but we've got something new here. We've got 3 resistors in series. And we know the current's going to be the exact same going through all of them, but how do we measure the resistors in series? Well, come to find out, it's actually not that difficult. In order to get the current in a circuit, we need to find the total amount of resistance in said circuit. And the way we find RT, or resistance total, is just by adding up the sum of the resistances in series. So let's take a look at this. We need some quantities for resistance. We'll call this 3 ohms, 4 ohms, and 5 ohms. That's lovely. So R1 is 3 ohms, R2 is 4 ohms, and R3 is 5 ohms. But in series, we can consider these resistors one big resistor. And the way we'd measure that is to add up those sums. So let's go 3 ohms plus 4 ohms plus 5 ohms. Simple math serves. Total resistance, or RT, is equal to 12 ohms. All of these guys right here can be seen, are viewed as one large resistor in the overall circuit. And if we could think of it as one big 12 ohm resistor, then we already know how to solve this. We've got V is equal to I times R to help us out. So let's plug and play this and see how this works. We know our voltage is 60 volts. We still don't know what I is, what we're trying to figure out, but we know our resistance is 12 ohms. All right, let's divide by 12 on one side, and we'll do the exact same on the other side of the equation, which means we've got 5 is equal to I. And we know we know current is always measured in amperage. So let's throw our A in there. And we know 5 amps of current are flowing through this series circuit. That was it. Good job, you nailed it. We figured out how to solve for current, but that's only really the first step. What we're going to want to do in a practical application is we're going to want to know what the voltage drop across our components is so that we could plan and design applications that fit their need. For instance, when I'm designing and building a circuit, I might want to know how much voltage is going across R1 or R2 or R3. Realistically, I'll probably want to figure that out for all 3 of my components here. And come to find out, we could do that, and we could do that easily with stuff we already know. Let's take a look at R1, for instance. It's a 3 ohm resistor, and we're curious about how much voltage, how much pressure is pushing across this resistor. Well, we can still use a VIR for that, but we're going to modify it just a bit. Because we're dealing with resistor 1, or what we've named R1, let's change it up just a bit. Instead of V is equal to IR, we're going to use the subscript V1 is equal to I1 times R1. And we use these subscripts to give us context. We know we're talking about this component of our circuit, R1. We want to know specifically the voltage that's going through that component. So we're going to isolate that and use VIR for that purpose. So let's plug in and see what we have here. We want to know what the voltage is that's going through this component. And we know that the current is 5 amps and the resistance is 3 ohms. I times R tells us that the voltage going through this component is 15 volts. Do you see that? 5 times 3. It's the current that we know is the same going through all of our components in series times the resistance that we've already figured out is equal to 15 volts. So let's just throw that one to the side. Say V1 is equal to 15 volts. All right, awesome. Now we got to do the same thing for the other two remaining components. Let's look at V2, because we're looking in context to our second component. We know that V2 is going to be equal to I2 times R2. V2 is what we're looking for. I2 is going to be 5 amps, and our resistance is going to be 4 ohms. All right. If we multiply that, we get 20 volts. V2 is actually equal to 20 volts. Are you guys seeing how we're taking V is equal to I times R, and we're just looking at it in context to each component one at a time? Lastly, we have R3. So we're looking for the voltage across R3. So we'll call this V3. We're looking at just isolating the voltage across this guy. All right. We know our current is still 5 amps. Our resistance is 5 ohms. 5 times 5 is equal to 25. V3 is equal to 25 volts. Now, I want to draw some attention to this right here. We see that we can identify the voltage for each drop in our circuit. But what do those add up to? 15 plus 20 plus 25. The total voltage, or VT, is equal to 60 volts. Well, let's take a look at this. Right here, our power source is 60 volts. And this is that Kirchhoff's law that I was talking about. I don't care that you know it in name, but I want you to recognize there's always this concept of balance when we're talking about circuits and electricity and energy. And Kirchhoff's law says that the voltage that flows into a circuit has to be equal to the energy that comes out of a circuit. This always applies to a closed loop, right? And that's exactly what's happening, right? We have these resistors that are using up energy. We have these components that are using up energy, and every bit of energy that's supplied by the power source. So that's a good way to check yourself too. I mean, in fact, even if you only found R1 and R2, you could just subtract those totals from the source voltage and figure out what R3 was without having to do the work for it. It's because there's going to have that balance. It's that seesaw effect all over again. And that's Kirchhoff's law. Voltage that flows into a circuit is going to equal the energy that comes out of the circuit. They essentially cancel each other out. One side of the equation is being consumed by the components, and the other side is the source. It's what's creating the energy. All right, guys, we've got one more layer to this layer cake that we got to get through, and that's the parallel circuit. It's a little different, but you're going to see how the premise is the same. This concept of balance is the exact same, even though the circuit is a little different. Let's take a look at what we have here. So we've got a power source, and instead of the current, instead of the electricity only having one path that it can go through, it actually has several different options that it can take. And this is going to change our approach just a little bit, but I think you'll see quickly it's not too difficult. It just takes reframing our thought process. So let's give some values so we can start solving this guy right here. First, let's name our components. We got our first resistor, our second resistor, and our third resistor, aptly named R1, 2, and 3. Let's give some values to this guy. We're going to make this a 12 volt power source. 3 ohms on R1, 4 ohms on R2, and 6 ohms. We'll go 6 ohms on R3. Excellent. Let's go back to what we were talking about earlier. A voltage across parallel resistors is the same. The current, excuse me, the pressure pushing across all these paths, just like we saw the picture of the tributary, is going to be consistent. It's going to be the same voltage across all these channels that the power can go through. What we want to do is let's figure out what the current flowing through each resistor is. Let's start there. Each resistor is considered being across this 12 volt power source. Let's isolate each channel almost as if it were its own simple circuit. And we can use our V is equal to IR again, and we're just going to add one little flare to it. If we're going to isolate these portions of the circuit in parallel, we can use VIR for that. And we're going to do somewhat like we did for the series, where we're just going to try and look at it in context to each section. So for example, we're looking at this first channel right here, and let's start throwing our equation together. V1 is equal to I1 times R1. Well, we know voltage across parallel resistors is going to be the same. It's the same amount of pressure pushing at no matter which channel or tributary you're in. So we can say 12 volts is equal to, we're looking for the current, we don't know that yet, but we do know that the resistor is 3 ohms. All right, let's do what we already know, making I1 equal to 4 amps. I hope that makes sense. I'm going to draw that here because I want to keep this in mind for this channel. 4 amps of current are flowing through this channel right here. We're going to duplicate this amongst all the channels. We're just going to change them in name. So V2 is equal to I2 times R2. This is resistor 2, this channel that we're looking at right here. And we know still 12 volts is equal to, we're trying to find the current, and the resistance in this circuit right here, this section of the circuit, is 4 ohms. Right, let's divide by 4 on both sides. 3 is equal to I2. So 3 amps are flowing down this channel. That's the volume of electricity that's going through this particular channel in the circuit. And then we've got one more to do. Let's go this guy right here. V3 is equal to I3 times R3. Again, we're just looking at this one specific channel of the circuit right here. 12 volts. We do not know the current, that's what we're trying to figure out, but we do know that there's 6 ohms of resistance, and we'll balance this equation, leaving 2 amps of current going through this channel. 2 amps of current. Now before we go any further, this is kind of a breakthrough moment that I want you to understand. I want you to see that as the resistance is increasing, there's more resistance to these channels no matter where you're at, or less resistance, the opposite is happening with the current. Through the first channel here, we see only 3 ohms of resistance, but we see the most flow, the most quantity of electricity going through. On the opposite end here, we've got 6 ohms of resistance. It's the most barrier to the electrical flow, and it's only got 2 amps of current. And here we're seeing again this principle of as resistance increases, the current decreases. It's like that if you were talking about channels, if we're talking about a water channel, it's getting narrower and narrower. The force might be the same. It's pushing the same amount of force. That's the voltage. But the flow, the actual quantity of water, is decreasing as the channel gets narrower. Okay, so with the information that we've already figured out here, we can start to decipher a lot more about this circuit. For instance, if I were to ask how much current overall is leaving the battery, what is the volume of electricity, of electrons or charge carriers that's leaving the power source? We know that now. And this is kind of like the flip side of the resistance in the series circuit. If we want to know in a parallel circuit the current, the volume of electricity leaving the battery, we can just add up the current that's in each of these channels. So let's take a look. If we wanted to find total current leaving the battery here, we'll call this IT. At this point, all we need to do is know what I1, I2, and I3 are. And they just so happen to correspond right here. 4 amps, 3 amps, 2 amps. That means the total amperage leaving the battery into this circuit is 9 amps. Alright, I'm going to bake your noodle just a little bit more and then we're done, I promise. I want to pose an additional question. Now that we figured out all the resistances, all the amperage through each channel, and we're now able to find out the total amperage, the total current, the volume of electricity leaving the power source, what if I were to ask you how much power is going through each junction? If I were to ask what the volume of electricity is at any given point between these junctions, you can actually figure that out. Let's go through this really quickly. I want to talk about one last concept of balance, and it has to do with current. Specifically, this is Kirchhoff's current law. And what this law states is all current entering a junction has to be equal to the amount of current leaving a junction. It sounds super cerebral, but when we see it in action in a moment here, it's going to make some sense. So what is a junction? These portions that I circled right here, these are opportunities for electricity or electrons to take one path or another. Call those a junction, right? We've actually already deciphered what the amperage is going through this channel, right? We know that there's 4 amps coming down this particular path, which means if the amount of current leaving a junction has to be equal to the amount coming into a junction, we can assume that 5 amps of current are carrying on. 4 is shunting down this way through this path across R1, and that leaves 5 amps left to go around the circuit. So let's take a look at this a little further. We also know that in this section right here going across R2, 3 amps of current are pushing past this section. Well, if we were to take 3 from the 5 that we have left going down this path. That means at this point, 2 amps of current are left. So let's go back through this one more time. Coming out of the battery, we've got 9 amps of current. 4 we know, we already solved for, are going down this first path. We've got 5 left, and then we've taken 3 amps from that 5, and we know it's going down that path. So that means we only have 2 amps left. And lo and behold, that's exactly the amperage that we solved for that was going past R3. The 3 amps comes back around, and sure enough, that's exactly what we solved for. But check this out. We're talking about the balance here. This is where it gets cool. We have a closed circuit, and everything's going in a loop, and it's feeding back into itself. So we've got 2 amps at this point between here and here. But we also have this amperage that's coming down, and it's looking to feed back into the negative terminal. And it's going to pick up these 3 amps. This 2 amps, these 2 amps here, and these 5 amps are going to join. Or, excuse me, these 3 amps here and the 2 amps here are going to join to create 5 amps at this section. And then the 4 amps at the end of this junction are connecting with the 5 amps here, making 9 amps coming back into the negative terminal. Well, that's exactly the flip side of the equation. 9 amps are leaving to go through the circuit to power the circuit. And 9 amps are coming back in. At every section of the parallel circuit, it mirrors the same amount of amperage is available on either side. I hope this makes sense, how this all feeds back into one balanced loop. We start with 9, and we're shedding off amperage as we go down one of these junctions, and then we have 5 left, and the demand for this component is 3 amps. It's shedding off 3 more amps. We've only got 2 amps left, but it's coming back and it's rejoining, because energy is never created nor destroyed. It's only modified, manipulated, or somehow changed, and then it's coming back to a full 9 amps back into the terminal. And that is it. Those are the high points that I wanted to hit for the chapter that I don't think the book really shed a lot of light on. I hope that we have a lot of folks joining us for the Wednesday live section, because I'm going to go through a couple of these problems together with everybody, and we're going to do some live demonstration and practical application. So I hope this makes sense. If you were kind of stumbling through the book, feel free to send me a message, email, or a Canvas chat if you need more help, and I'd be happy to answer any or all of your questions. Thank you so much. Have a good one. Bye, guys.